Hey, good morning.
Hi, Patrick.
Hey, buddy, I got you some craisins.
Thanks. Hey, here's your coffee. Irish coffee. Wink, wink. Hey, where's Greg?
I saw him out front. He's right behind me.
Sorry. Hey, good morning, guys.
Hi, here's your Diet Coke. The first 2 liters, just the way you like it.
Thanks, buddy. You are the best.
We got to plan today's episode, and then we need to think about some future episodes.
Jiffy, do you have a list from the email requests, the web portal stuff, whatever Twitter DMs might have come in?
Yes. I should maybe warn you that we get a lot of, questionable messages and requests.
Ho-ho! What you got?
Okay. Dynamic structural equation models. Porn. More porn. ANOVA table interpretation. Porn. Partial and semi-partial correlations. Porn.
No.
Someone asking you guys to help them with a 3-way interaction isn't porn?
That one actually could go either way.
Intensive longitudinal designs. Mixed methods. Porn. Meta-analysis. Porn. Porn.
Actually, that last one's also legit.
Actor-partner modeling is a real thing?
Yeah.
Sounds kind of suggestive. Anyway, statistical degrees of freedom.
Ooh, hold up there, Jiffy. I like that one.
Me too. What?
Well, it's just that, you know what happened the last time you did something related to degrees of freedom? What were they called?
Researcher degrees of freedom?
Researcher degrees of freedom. Ooh, some people on Twitter did not like that one.
Yeah, we know.
Have you seen some of the DMs that came in? Here, take a look.
Oh, I hadn't seen that one.
Yikes.
Never mind. I really just think we should do statistical degrees of freedom.
Totally agree. It's a very cool topic, and it's not really well understood.
Well,
Come on, let's do it.
Yep.
okay. Team Quantitude on 10.
Just do 3.
3 on 10?
Team Quantitude on 3.
What?
Never mind. Go team.
Yeah. Go team. Okay, guys, give me 5. I got to refill my coffee and Google degrees of freedom.
Okay, guys, have a great show. And for what it's worth, I don't think you're total... Wait, what was it? Oh, yeah. I don't think you're total asshats. And we're live in 3, 2, 1.
Welcome. My name is Patrick Curran, and along with my friend who is characterized by way too many degrees of freedom, Greg Hancock, we make up Quantitude. We are a podcast dedicated to all things quantitative, ranging from the relevant to the completely irrelevant. In today's episode, we talk about degrees of freedom, what they represent, how they are computed, and the importance they play in daily life. Along the way, we also discuss color blindness, the Skinnylicious menu, Kevin Bacon, Elmo's Diner, the Flatties, Amtrak, drinking Guinness at room temperature, sudoku, courage, paying the reaper, Karl Popper's corpse, needing 152% on your final exam, and famous grandfathers. We hope you enjoyed today's episode.
I have a story for you.
All right, because I'm settling in with coffee and I need a few minutes, so go for it.
Okay. Goldie and I are in spruce up the home kind of mode. Usually that seems like a spring thing to do, but we're taking care of some repairs, doing some things that we've wanted to do. And one of the things that we want to do, one of the things I want to do is to paint the inside of the garage. It looks terrible. Paint peeling off the walls, plaster coming off, and all that. So we went to Home Depot to take a look at paint.
Let's do this. That's the power of the Home Depot.
And for anybody who has ever gone to a paint store or the paint section of a store, there is an ocean of options. All the little paint chips that they, I guess, want you to take with you and go home and mull over, right?
Mm-hmm.
I'll remind you that this is for our garage where we put cars. That's okay. Okay, so we stood there at Home Depot looking at the paint options for an hour and 15 minutes for our garage where we put cars. And so we're like arguing, do we get Skylight Rendezvous? Or what about Lilting Laughter or Infinite Cumulus? All these different names that mean nothing. And we're arguing about that. And we were just completely paralyzed by all the choices, right? And you could just see them, hundreds and hundreds and hundreds of choices there in front of you. We had, I think the term is analysis paralysis, right? We just literally couldn't decide on which one until finally we reached an agreement. And you know what color we agreed on?
I would have gone with eggshell white.
Right? You're very close. After all of this consideration, gray. And you know why we went with gray? Because it's a garage where we put cars. And the best part of the whole story, Goldie is colorblind. So huge chunks of these look the same. And we're arguing for an hour and 15 minutes. And ultimately we come up with gray.
The moral of the story is you could have painted it any color you want and just told Goldie that it was gray. You know, the thing I like about those paint swatches is it's almost like a federal jobs program for English lit majors for naming them.
What am I going to do with my English degree? Well,
I'm going to have whisper raindrops. It doesn't matter what color it goes to. It's just whisper raindrops.
Uh-huh. So that was the fun that I had with hundreds and hundreds of choices to decide on gray in the end.
Yeah, I have similar experience when we every now and then go to Cheesecake Factory. We went there a couple of weeks ago, and they have an outdoor patio, and so we went to eat outdoors. I don't know out there who of you have gone to Cheesecake Factory, but they have a tome menu that is bound and looks like the original version of the Dead Sea Scrolls as they set it in front of you, this like New York phone book. I'm not an indecisive guy. I'm really not.
Uh-huh.
I just need a small denominator.
Yeah.
And what I've come to there is they slip inside a healthy choice option little flyer, which of course there are like 3 things on it because you're at, well, Cheesecake Factory.
That's right.
But I set aside the phone book and will order off of the healthy choice menu just because it has a smaller denominator.
Not because of your commitment to the Skinnylicious options.
Nope, it's just there are just fewer of them. Sometimes in life, we just need smaller denominators.
In fact, in marketing, I think this problem is really well known, that if you have too many options when customers come into the store, they can't make up their mind and they leave. But if you have fewer options for them to choose from, then maybe you can actually get them to buy something. So for me, what is the segue here?
I'm patiently waiting.
It's the idea of, wait for it, degrees of freedom. What do you think?
Going from color blindness to degrees of freedom. If we can only link it to Kevin Bacon, we'll be set.
Let's dance! Now I gotta cut loose.
Yeah, so degrees of freedom, having a lot of them, having not very many of them, degrees of freedom is a topic that I will just confess right now. I talk about, I teach about it, I use it in all kinds of things, but at least at a certain point in my life, I would have been really hard-pressed to explain it. And I think if you leaf through a lot of textbooks, they pretty much phone it in when it comes to the explanation.
And not always correctly.
Oh, absolutely. Right? When we read an intro textbook and the description of degrees of freedom, the things that we get are lame at best and wrong kind of at worst. There's a statistician, Brian Everett, and he wrote an entry in the Cambridge Dictionary of Statistics where he had to provide a definition of degrees of freedom. And his definition was an elusive concept that occurs throughout statistics.
Wait, you're allowed to write that?
Yeah. And I will tell you, some of the explanations that we give for degrees of freedom, which I'm sure you and I will talk about here, have a really nice intuitive feel. But what the heck they actually have to do with statistics and why, I think, is still sort of disconnected.
You know what I find so interesting about the topic, beyond the things we're going to talk about, of just how terribly important it is to everything that we do.
Yep.
And you can trace lines back to Pearson and Fisher and Student. And I mean, this is like big ticket stuff.
Oh, yeah.
And absolutely, it is elusive and complicated and vexing. But in a way, it's not. Mm-hmm. One thing I love when thinking about stuff that you and I talk about and other stuff in our day job is how often these things live in the wild around us in silly little ways, but that are the concept that we're talking about. We talked on an earlier episode about you go to Elmo's Diner and there are 4 of you at a booth, right? And they come up and say, Who has the pancakes? Who has the eggs? Who has the waffles? There are 4 people, 3 plates are down, and someone says, and who gets the blueberry pancakes? And then you have a sarcastic 7-year-old who rolls their eyes. That's degrees of freedom. Another one is who out there, let's be honest amongst one another, right? We're getting to know each other well. And I think we're getting to a point in the relationship where we can be honest with one another. Who out there has not gone into a final exam having calculated the exact score that you need so that you can get a B- in the class?
The B- was really good for you, Mr. C+.
I never overreached. Don't be greedy. But you walk in at 8 a.m. and say, all I have to do is get 152% on this final, and I'm going to get a B-. But if any of you have ever calculated the score that you need on a final exam to get a particular grade in a class, that's degrees of freedom.
It is absolutely a degrees of freedom thing, and yet, what the heck does that have to do with statistics, right? And that's really the issue. I think when we explain degrees of freedom, we say things like, oh, the server brings 4 dishes, lays 3 down, and obviously the last one is determined. But we have to connect that to statistics, and I think that's where a lot of books sort of fall short. There's a really, really nice quote by an author named Chung-Ho Yu, who referred to degrees of freedom as an intimate stranger.
Ooh.
There's some people who say that I don't have a heart.
Why would they say that?
Because they know me well.
You have a lot of familiarity, you have a lot of experience, and yet, do you really know it?
That is really good.
Are you okay if I just poke at your brain for a little bit?
I mean, it's an unfair fight because you insist on recording these at 8 in the morning.
All right, so I would like to take you on a slow journey to deepen our understanding of degrees of freedom.
Do you need me here for this?
All right. So first of all, I want to think about degrees of freedom as how much freedom there is for things to move around. I know that's incredibly abstract, but imagine that there's a mosquito buzzing around the room. That mosquito has freedom to move around in 3 dimensions. We could say it has 3 degrees of freedom. So I want to tie this idea to dimensions. If we have a drop of water on a plate and we move that plate around a little bit, that drop of water is moving around in 2 dimensions. Or if we have a drop of water on the surface of a basketball and we keep moving the basketball around, that bead of water, even though the basketball is in 3 dimensions, that bead of water is actually moving around in 2 dimensions. And that takes a minute to get your head around, but it's actually kind of important because as far as the drop of water is concerned, it only knows movement ahead and back or side to side. So the idea that even though the world around it is in 3 dimensions, from the drop's perspective, it's in 2 dimensions. When I was in college, we used to refer to the flatties. The flatties are these little imaginary creatures that live in a plane, but that plane is in a 3-dimensional world. But they can only move in the plane, and they don't even know they're in a 3-dimensional world. To make even a bit more concrete, think about a train on a train track. And the train track itself exists on the surface of the Earth, which is a 2-dimensional surface, where the Earth exists in a at least 3-dimensional universe. But at the end of the day, the train track is 1 dimension. The train can go forward, the train can go backward.
And if it's Amtrak, it can go sideways.
You had to do that. If we specify some distance from where the train left, right, we say 5 kilometers, 8 kilometers, 30 kilometers, then we can locate the train exactly. So it is in only 1 dimension. It has only 1 degree of freedom. So I want to connect the idea of dimensions and degrees of freedom. Imagine we have 2 scores, and their average is 5. What does that make their total at 8 in the morning? Come on, quick. What does that make their total?
10.
You're functional.
It's sample size times the mean equals the sum.
Nicely done. So that means that if we have an axis that represents all the possible values that x1 can be, x1 meaning the first observation, and we have an axis that represents all the values that x2 could be, if we didn't know anything about the mean, then we would just say those 2 scores can roam this space and be anywhere, like the little flatty mosquito flying in that plane. But now if I tell you they have an average of 5, or as you said, rightly, a sum of 10, then we know that they're going to fall on a line that will have points like 19, 28, 37. It's going to define a line that goes from up toward the northwest down toward the southeast. That means now that there is only one dimension in which the scores vary. It's like the train, right? That even though it exists in a broader space, they're only traveling along one dimension. So we would say in that system, and I'm trying to be really careful with my language, that there's only 1 degree of freedom. What do you think so far?
Yeah, I'm with you.
So this idea extends, of course, into more dimensions. Imagine you had 3 scores, and just for simplicity that their mean is 0. That means that their sum is?
0.
There you go. What that means geometrically is if you think of an axis for the score x1, the first score, and an axis for score x2, axis for the score x3, those scores now vary in a plane because we have a fixed sum. One of the dimensions really winds up being completely dependent upon the others. So now even though x1, x2, and x3 conceptually exist in 3 dimensions, they can only move in a reduced space. Now, one of the points that I want to make early is that it's not the scores that have the degrees of freedom.
Is this going to be another one of those things where we teach something in a particular way to foster understanding, and then we criticize students for not understanding the real issue at hand?
That's right, because they repeat back the way we exactly said it, and then we tell them, well, that's not exactly right.
God, I love this job.
It's the best. It's the best. Yeah, so if I tell you there are 3 scores, those 3 scores don't know that you've computed the mean, right? They're not like, shit, did he? I don't know. Am I free to vary? Am I not free to vary? The scores don't know that. The scores exist out there. So it's not literally the scores that have the degrees of freedom. It's going to be something that has the degrees of freedom. And I think that's partly where we don't finish the job. What we've talked about so far is a server who knows what to do with the blueberry pancakes. We've talked about points that move in reduced spaces, but we haven't actually connected it to statistical things other than, and the mean is 5, so what now?
I love everything you're doing here, but when we compute a sample variance and divide by n-1, how does this map on? Like there's a fog of war here for me.
So you're just being impatient and you can't wait for that? Is that it?
That's one way of saying that. I mean, if you wanted to be accurate about it.
Fine. Are you ready?
Yes, please.
Okay. Okay. So we encountered degrees of freedom really in 2 places. And one has to do with when we divide things to get variance estimates. And another has to do with something that seems different, but it's not, when we choose the distribution that we go to for our test statistic, right? That some of the distributions, not the normal distribution, but some of the distributions that we appeal to have degrees of freedom associated with them. So how do we connect flatties and dividing by n-1? All right, here's what I want to do. I want to go back to the 2 scores that we talked about before. And as you said, if we know the mean, the first one can be anything. The second one is totally on lockdown, right? Has to be a certain thing. What does that mean in terms of their deviations from the mean? Let me ask you.
It's the classic thinking about the mean as a balance and fulcrum, and that the mean is the center of weight. So you would have one is positive and offset and one is negative and offset to the exact degree where the mean is the balance point of the 2.
Perfect answer. Full marks. I think you're going to get that 152% that you need. 152%. I think it's going to happen. I'm feeling it. Yes, that's exactly right. So that when you have these 2 points, the deviations are equal and opposite. And what that means in terms of the square deviations is that they are completely equal. If I know the square deviation of one score, then I know the square deviation of another score. Now, when we talk about variances, what we do is we add up all of the square deviations. And if I were computing square deviations from the population mean, mu, right? So I draw a sample of 2 scores, doesn't matter, and I compute the deviations from the population mean, those 2 deviations wouldn't necessarily be equal.
That's right, because they're random draws from some distribution that happens to be characterized by mean mu.
That's right. Knowing the population mean puts no constraint on them whatsoever, so that those square deviations are free to be whatever they need to be. In fact, the deviations could both be positive. The deviations could both be negative, so that the square deviations have no connection to each other, completely independent. If I wanted to take an average of the square deviations, it would make sense to divide those by 2 if I'm trying to estimate how scores vary in the population. But if I don't use that population mean, and I use the sample mean, all of a sudden things change. As you said, the 2 deviations are equal but opposite. The square deviations become identical to each other, and now they're not functioning like these independent things at all. They function exactly like one thing. So if I add them up, big deal that I added them up. I just added up the same thing twice. There's no new information provided by that. So even though I had 2 observations, they are functioning as one. When we say, what does that tell you about the population variance? The answer is, well, it doesn't tell me 2 scores worth of stuff. It really only tells me 1 score worth of stuff. When we compute an estimate of the variance in the population, but we use the sample mean, we divide by the effective sample size, the number of those square deviations that were really free to be different from the other square deviations, the number of those square deviations that are contributing unique information. And that is a reason why we have n-1 in the denominator.
The other reason is the mean costs you $1. Right? So if you're going to compute a sample variance, so everybody picture in your mind's eye, sigma paren y minus y bar paren squared, right? That's the sum of the squared deviations. You have to buy that mean. And it's going to cost you $1. And that $1 is 1 degree of freedom. And if you're going to compute y minus y bar, well, you got to go out and buy that mean first. And so do you divide by 2? No, because you had to pay $1 to get y bar. It's 1 value less than the sample size that you observe. So it is n-1. You can tell my understanding of statistics verges on superficial.
So we had pancakes and paying $1, and what else did we have?
152%.
152%, yes. Good. So you're absolutely right that there's a cost associated with it. You pay $1. And the reason you pay $1 is because that sum of squares no longer contains information associated with that full n. And if we tie that to a distribution, there are different ways we can tie that to a distribution. One of them has to do with a chi-square distribution. We had a pop quiz
So, if I may interrupt briefly, I would say with the greatest support and friendship possible that you gave arguably the worst response in pop quiz to the chi-square distribution, in large part because of your complete and total failure of bringing in degrees of freedom. Now, you also were talking about Karate Kid, my bromance with Kai Ryssdal, so we won't talk about clock management, but it's just funny, your abject failure of responding to the chi-squared question did center around degrees of freedom.
Yeah, was it worse than my Bayesian answer that I gave last season?
Yes.
Wow!
Well, you were throwing around terminology I didn't understand with the Bayesian answer, and so I really couldn't pinpoint why I thought you were gaslighting me.
Just seemed like crap. All right. So, no, I trust you are right that I didn't bring in degrees of freedom. So let me make amends right now.
Okay. You're going to do penance because that came up as well.
All right. This is it. So the chi-square distribution can be thought of as a distribution of a sum of squares and how a sum of squares fluctuates when that sum of squares contains independent information. If we wanted to think about it in a standardized metric, we could think about those squares being standardized, and then it would be like the sum of a bunch of z-squareds, where all of those z-squareds were completely independent. So if I go back to the example that I gave just a couple of moments ago, if we have 2 scores and we compute their deviations from a population mean, those deviations are independent. So their square deviations are independent. So if we computed z-scores relative to that population mean and squared them, they would be independent of each other. A chi-square of their sum is like a measure of how weird are those 2 scores? How weird is it that you drew those 2 scores from that population? So it's this overall measure of weirdness, which we might call badness of fit. In the case where we form those deviations around the sample mean, though, What we just learned is that those two square deviations are going to be identical to each other. And if we tried to standardize them and create some version of z-like scores and square those, we could sum them up as well, but they're not going to function like two independent squared z-scores. They're only going to function like one because they're going to be identical. The chi-square distribution that would follow would only have 1 degree of freedom because there's only one piece of information that's being brought to bear, that's being summed up. We might be adding it up twice, but the appropriate distribution in that case would only have 1 degree of freedom. Whereas in the case where we formed the deviations from the population mean, the scores were both free to be whatever they wanted to be, and that would have 2 degrees of freedom. So the chi-square has a number of degrees of freedom that can be thought of as the number of independent pieces of information going into that numerator that in the end are squared and summed up. So is that enough of a tie to degrees of freedom or not yet for you?
That was vastly improved. It's hard to think about how it couldn't be, but I like that a lot. Could I throw a monkey wrench into the gears a little bit? Far be it from me to ever do that during our discussion. I would like to teleport back in time a little bit and talk about Guinness beer. I think this is probably where we really need to talk about Guinness. And should that be consumed at room temperature? Or should that be chilled? Because I got to tell you, if you go to a pub in a small village in Ireland, that comes to you at room temperature. And we could dedicate an entire episode on the Americanification of Guinness beer. Why I raise Guinness beer is Gossett, and Gossett back to Fisher, and Fisher back to Karl Pearson with a K. Because one of the really interesting things, and we puzzled through this during the summer history episodes, is Pearson with a K. Remember, there was Pearson Jr.,
Egon
Pearson. So he's not really a junior. Pearson 2. We got Pearson 1 and Pearson 2. Pearson 1 had a mind-numbing insight that impacts everything every one of us does on a daily basis. And we won't revisit it here because we talked about it over the summer. But the notion of going from the observations that we obtain in any scientific endeavor and using those as a mechanism to get to the parameters that govern the distribution that gave rise to those observations. And often this is viewed as the start of what's sometimes called the statistical revolution, as moving from the observations for the sake of the observations to using the observations as a ticket to get into what Pearson developed as the 4 moments of the distribution: mean, variance, skew, kurtosis. He never talked about degrees of freedom.
Right.
And indeed, it's unclear if that was ever on his radar, because he believed that if you got enough observations, you could get these population values.
Right.
And that's where Guinness comes in. And Gossett and Students T was like, dude, I won't do the Irish accent because it'll just come out as a pirate. But Gossett saying, dude, I've got 20 samples of yeast and I compute a mean, and these means vary all over hell's half acre. And I've got to somehow take account of that. And one of the biggest changes that we had in moving from Pearson to Fisher to Gossett was the very notion of degrees of freedom.
Yeah, so that when you compute a test statistic for testing a particular sample mean relative to a population mean, when you have a huge number of observations with your Pearson hat on, it's like you basically know the answer. But what Gossett was trying to realize is that, yeah, these things are not going to follow a normal distribution anymore. They're not even going to come close to approximating a normal distribution. So when we say the t-distribution, that's kind of a misnomer as it is, because the t-distribution is really a family of distributions, each one tailored to a different number of degrees of freedom, which we attach to sample size. And his huge insight, although it was really very limited to those kinds of tests that we're talking about right now, was that A, you can't use the normal curve, and B, you need to adjust what curve you use specifically to take into account that you don't have population quality information here.
And that brings in the asymptotic mathematical statistical concept of paying the reaper. Because any of you who have had a decent stats class has seen a plot where it has a z distribution. There is one z distribution, and it's defined by mean mu and standard deviation sigma. All right, there's one that lives out there in the wild, one z distribution. There are an infinite number of t distributions, each of which is defined by a unique degree of freedom. There's a t distribution for 1 degree of freedom, for 2, for 3. And if you had this in class, someone overlaid maybe 3 or 4 t distributions, one with 3 degrees of freedom, one with 5, one with 10, one with 20. And a couple of things you see is the fewer degrees of freedom there are, the less certainty there is about that distribution. It's flatter and has thicker tails as they go out. Why? Because if you're trying to estimate a mean with 3 observations, well, let's all be honest with one another. You're doing a pretty crappy job, and you got to pay the reaper for that. What about 6 observations? Still kind of a crappy job, but it's better than 3 observations. What about 12? What about 18? What about 36? What about 72? Well, your precision goes up and up and up, and those t distributions go to the z. Now, never will it actually reach it, but it will get infinitely close to it. That brings in the pay the reaper. If you've got a sample of 5, you got to pay somebody for that lack of precision, and that's by using a t distribution that represents there's just a boatload of variability among those means.
Just to be clear, do you pay the reaper $1? Is that?
That's a really good question. I don't think so.
Okay, because I'm...
The payment is more ethereal.
Okay. Yeah, there's a lot of payments changing hands here.
There is.
Not exactly.
Stay with me, Hancock.
Okay.
It's 8:45. I'm waking up.
God help us all. So the insight that Gossett had, the funny thing is that Gossett really sort of only thought about it in the context of that t distribution, right? And it was Fisher who was ridiculously smart and by all accounts equally unpleasant.
Horrible human being.
Who saw that this actually applied to a lot of things. And a lot of things that, I mean, Pearson, as you said, didn't really understand this. And so Fisher took opportunity in things that he wrote to poke at Pearson, and Pearson didn't see that, and Pearson didn't see this. But Gossett's paper was in 1908?
Yes.
And so then Fisher came out in 1915, where he was talking about the sampling distribution of correlation coefficients. And he sort of formalized this broader notion of degrees of freedom, which ultimately led us to chi-square distributions and led us to F distributions. In fact, F distribution named after, not invented by technically, but named after Fisher. And the idea of what you said, there being an infinite number of t distributions, is really, really cool because as you go down any column of a t table, or if you think about those t distributions as you described, at some point they're basically a normal distribution. And that's because the more information you have, the closer and closer and closer your sample statistics get to approximating the population. From Pearson's point of view, it's like, yeah, they're basically population. But we know with your sample of 3, they're terrible. And the reason the correction is n-1 in that case, for example, you can think about it in 2 ways. One was the reason that I gave before, that the last square deviation is really just a function of the other square deviation. So there aren't as many things that are literally free to vary in the system. But you can also think about it in terms of bias. And this was actually the way I first learned about degrees of freedom. And that is that the principle of least squares, the idea that if we take the sum of square deviations around a mean, a sample mean, it is going to be the smallest that it could possibly be. And if the population mean is anywhere else in the world, which it almost certainly is, then your sum of squares around your sample mean is going to be too small relative to the sum of squares around the actual population mean. And if you figure out how biased it is, how biasedly too small your square deviations around the sample mean are as a representation of how scores vary around the population mean, it turns out that when you have a very small number of scores, it can be really biased. And when you have a really large number of scores, not so much bias. And mathematically, what you can show is that the exact divisor is n-1. And it is for the reason that you paid $1. You paid the Reaper, you put 3 of the orders down, and the last one was blueberry pancakes, that of all the things that were free to vary, that last one was completely dependent upon the others. And that corrects the bias that you have to give you an unbiased estimator of variance.
And you did wonderfully, except you left out equity.
Okay.
So imagine, and I'm going to restate what Greg said, but just in highlighting a super important point, because there is a practical aspect to all of this. There's a beautiful, asymptotic, elegant, mathematical stat version of this, of degrees of freedom and limits and central tendency and variability. But all of us are doing research, and all of us are trying to determine within some reason, is this a significant effect? Is it not a significant effect? And so from a practical standpoint, imagine you're trying to estimate a variance and you have a choice of dividing between 5 or dividing by 4, right? If it's n minus 1. Well, the difference between dividing by 5 and dividing by 4 is pretty big, and you really got to pay attention to that. Now, what is the difference between dividing by 5,000 versus dividing by 4,999? Who cares? Nobody cares. It's going to be out in the 5th decimal point. And so what you sometimes see is actually a little bit of carelessness on our own part as applied researchers. I have had in class where people say, well, if you have more than 20 observations, just use a Z distribution because they're functionally the same. And point 1 is, yeah, they're pretty close, right? Often we'll say, well, we're looking for critical ratios plus or minus 2. Right? That'll more or less give us the interior 95% of the distribution. But they're not the same. And you got to respect Guinness. I think that's what it goes back to, is you have to respect Guinness. Is Gossett is in his grave saying, arg, you should drink it at room temperature, but is also saying 20 is not close enough for government work. You need to calculate that T based on the n minus 1 because we're not just shrugging and saying plus or minus 2. We need to know what these values are.
And the idea of equity extends into our regression world, right? When we talk about residual variance, we have learned that the residual variance has in its denominator not n minus 1, but it has n minus the number of predictors minus 1. And we even coach ourselves into saying, well, that's because we lost 1 degree of freedom for every slope and 1 degree of freedom for the intercept. What that means logically, and this is a fun game to play that would torture Patrick in ways that would be simultaneously fun for me and just awkward for everybody out there. But if I told you that we had a regression line and I gave you a very specific regression line, this is it. This is the slope and the intercept. And if anybody out there wants to play this on their own, make it simple for yourself and make the slope and intercept 0. So you've got the perfect regression line. We will say for 3 points is a flat line at 0. And I'm going to tell you that your x values are 1, 2, and 3 to make it simple. And I'm going to tell you that the deviation from the regression line for the very first point, I'm giving this to you, is -1. So the first point falls 1 unit below the regression line. And so now I would ask you, where is the point for when x is 2? And where is the point for when x is 3? And the answer is they're already determined. There's only one choice on God's green earth for where you could put the next 2 points so that that is, in fact, the regression line. I'm not going to torture Patrick with figuring all of that out, but if anybody wants to play with that, draw yourself a flat line, put the first value at x is 1 as 1 unit below, and then you figure out what the next 2 values are. And it might feel in your gut like, oh my gosh, the second one could be anything. Second one can't be anything. You put it anywhere you want, you're probably not going to be able to find a place where you can put the third point in that x equals 3 column that's going to bring the regression line to where you want it. So the idea of you paying $1, or in this case, a couple of bucks, or paying the Reaper or whatever, it holds when we extend this out to more dimensions, because we have placed more constraints on the behavior of our data. In this case, we said, yeah, they have to have a slope and they have to have an intercept. But technically, you're not putting constraints on the data. You are imbuing your variance estimate with those constraints so that your residual variance in the end is not based on 3 residuals. I know it feels like it is, It's based on one independent residual and two others that were completely determined by the first one. So these ideas extend out to all different dimensions, not just for our simple little toy example of if you have two scores and the mean is the following. This extends throughout all of our general linear model.
It's very much like a Sudoku puzzle. So my wife is addicted to Sudoku puzzles where, they put a couple of numbers in the rows and columns, and then you have this grid and you have to fill in the numbers.
There are no degrees of freedom in terms of the answer.
That's right. The other night, my wife was doing one of these at the kitchen counter, and one of my teenagers came into the room and behind my wife's back pulled out the orange juice and swigged directly out of the bottle while looking at me conspiratorially and put it back. And she walked out of the room. And as she was walking down the hallway, my kids said, "The 9 in the upper left quadrant is in the wrong place." And the string of profanities that came from my wife.
And speaking of your wife's profanities... No. But speaking about systems where there might be only one solution, as in no degrees of freedom, that actually translates really nicely to the way we think about things when we're doing models. Now, you and I mean, everything that we do is a model, right? That's what we do. We model full time.
Yes, beautiful, feeling it. Okay, you're an animal. Yes.
What you and I do in particular is we do a lot of structural equation models, growth models, and things that tend to be in that particular family. And we talk about degrees of freedom in that world all the time. And we do it almost in this entirely different way, right? It's not about going to a chi-square table or a t table. We don't usually think about it as n minus something when we talk about degrees of freedom. We think about degrees of freedom in a different way in this world.
That's right. Okay, so it's becoming clear even to me that I don't understand very much about statistics because we talk about degrees of freedom as courage. Right? Because what we've talked on prior episodes is if you think about why do we subtract 1 from n, right? Mm-hmm. The -1 represents one restriction that we've imposed on the distributional space. And that restriction is we know what the mean is, all right? Mm-hmm. But that scales up. And degrees of freedom then start representing number of restrictions or is related to number of restrictions. So we work in a world where more degrees of freedom are good, right? If we're talking about a Karl Popper a priori power model testing kind of thing, degrees of freedom, more are good. And it's interesting because if you delve into the stats literature, there actually is, and it's not used colloquially, it's a real term of thinking about degrees of freedom as optimism. Mm-hmm. And it's not dissimilar from courage, which is capturing this estimate of appropriate variability. Mm-hmm. But my colloquial definition of degrees of freedom, if you think about it broadly, are the number of pieces of information that can vary freely under a set of constraints. Mm-hmm. That's how I think about it. Because everything we've been talking about so far has been individual observations. Those are the pieces of information that can vary freely. But what you're moving to is if we move into our world of structural equation modeling, the pieces of information move to variances and covariances and means. Mm-hmm. And we can recast this entire conversation in terms of the ability of those pieces of information varying freely under a given set of constraints. And those constraints are our model.
And all of those have anchors to distributions because the distribution of scores is governed by variances, covariances, and means. But it's very convenient for us just to think about it exactly as you describe. So if I ignore the means for just a second, if we have p variables in a model, we have p times p plus 1 over 2 variances and covariances in our data. So how many parameters do we have in our model whose job it is to explain those p times p plus 1 over 2 variances and covariances? Well, if you have p times p plus 1 over 2 parameters in your model, guess how well you're going to do.
This is another example of where we teach it in one way to try to help foster understanding, but it's really operating in a very different way. We've talked in prior discussions about how all of us, when teaching regression, is we have our observed variable y and our reproduced y hat, and we have y minus y hat as our epsilon, and we square it and we sum it and we get the smaller. We don't do any of that in the estimation. It's all moving those conditional means. If you give me a covariance matrix and a mean vector with no individual observations, I can do a complete regression. So you are exactly right. All of these are tethered to distributions. But it's more salient in the SEM where we talk about how many independent pieces of information did you observe. So I'm with you. Let's ignore means. So we have p times p plus 1 divided by 2. Those are the unique elements in a covariance matrix. Those are our dollars in the bank, right? That's our money. Those are our independent pieces of information. Every restriction that we impose in our model, every parameter we estimate, every equality constraint we put on, every parameter we remove, we've got to pay out of our bank to get those parameters. And what you described of what if you have p times p plus 1 over 2 estimated parameters, well, we talk about that as a saturated model. That's complete lack of courage. If you observe 10 things, you estimate 10 things. You have no degrees of freedom. You observe 20 things, you estimate 20 things. You have no degrees of freedom. Oh, why would we ever do that? Why would we ever do that?
Gutless.
We do that in every regression model that has been run since Yule.
We do. And there might be reasons. The reasons associated with regression are because that's the way regression's made. Sometimes we have models that are saturated, that theory would defend that every single connection, every single parameter that we have in there is completely backed by theory. Okay, then your goal is no longer to assess the theory. Your goal is just to estimate the values of those parameters, given that that is a reasonable theory. And Karl Popper in your backyard issues a groan from beneath the earth.
That's exactly right. Because regression really truly is rescaling variances, covariances, and means in a way that means something to us. So if you have X predicting Y, that regression coefficient is the covariance between X and Y divided by the variance of X. We're rescaling that covariance in a way that has some meaning to us. Now flip that arrow and you have Y predicting X. It's the covariance of X and Y divided by the variance of Y. It's the same covariance. You're just rescaling it in a way that's of some use to us. Now, you and I both love regression. We're not bad-mouthing that at all. But holy cow, it is like the Cowardly Lion doing his dissertation.
Put him up.
Estimate them all. Come on, estimate them all. Right? But let's try to tie back then. Tell me why in that scenario are degrees of freedom good?
Yeah, that is a good question. And there are a lot of different ways to answer it. We could go at it computationally. We could go at it abstractly in terms of courage. I think at the end of the day, a philosophical answer is probably the best. And that goes right to the heart of what you were saying with regard to Popper. If I have a theory that says I can explain 10 phenomena in the world using 10 characteristics of the world, then people are just going to go, whatever. If someone, on the other hand, says, I believe the variances and covariances in the population should be the following, and they actually give you numerical values. So if you got a model with 4 variables, the person says, I think the 4 variances should be this. I think the 6 covariances should be this. And if we want to have means in there, then God bless us. I think the 4 means are this. So someone comes at you and says, this is my strong theory, and tries to assess the fit of those numbers, those fixed parameters, to what we observe in the sample. That is the most courageous person of all. That is a person who says, I am going at this with no free parameter in my model, every single thing is fixed. So because that model has 0 parameters to be estimated, it has the most degrees of freedom that any model could have. The difference between the number of observed variances and covariances that we have, our money, and the number of constraints we're trying to put on that is as big as it can possibly be. I would say in terms of your courage, that is the most courageous we could possibly be.
And historically, that maps on to centuries of really interesting anecdotes about using mathematical models of the universe and the implications for where does the sun reside, where does the moon reside. We've talked before about Leverrier, who derived mathematically the existence of Neptune because he applied the mathematical model, no estimation. He applied the mathematical model to lay out the orbits of planets, and it didn't match the observed data. And he put in a mass of a body that had to be there to account for those perturbations in the elliptical orbits, and that was Neptune. So I think it's a really nice starting point of saying, if I'm right, if my theory is right, so paraphrasing Popper, as he said at one point, that we should all put our theories in mortal danger on a daily basis, is you fix everything to predetermined values that are consistent with theory and then compare that to the characteristics of the data. That absolutely is the most courage. Because the other end of that continuum is, oh, I have no freaking idea, I'm going to estimate everything. That is the multiple regression model. So then you have no degrees of freedom, or you have as many degrees of freedom as are possible given your measured variables. Like everything, we probably want to live in between those two bookends.
I would say maybe. It depends how you view it, right? An argument could be made, and this is part of maybe a larger conversation, that we start off observing the universe and seeing relations and maybe supposing patterns, and then getting a little bit braver and saying, well, maybe this restriction is sort of governing what's going on. And then maybe this other restriction. So in many cases, I would love to see us even make a stronger move toward models that are more courageous. You know, we seldom end the story with, and we now believe that this is the parameter. Right? Instead, we end the story with, and now we believe this is the model that governs what's going on, but we're just kind of going to estimate the values for those things. So we do wind up living in the middle, but I still think it would be nice if we could make the journey from not knowing what the heck is going on, which is in many ways a 0 degree of freedom situation, to where we understand it completely and we think that we know everything at the tip of our pen.
I couldn't agree more, because Leverrier got the orbits that he fit his mathematical functions to by observing them at night. Not him. He hired a whole bunch of people to go out in 20-degree weather and try to map these. But we're wandering into the inductive, deductive. We can think about what is the purpose of science: observation, prediction, explanation, manipulation. That's another colloquial way of thinking about it. As observation is, oh, look, this planet goes around and around and around. And prediction is, oh, I bet tomorrow night it'll be here. And explanation is, well, this is why, because there are these joint gravitational forces. And manipulation is, oh, crap, we don't do that in astronomy. So it's always about this point in the conversation that I feel like I need the Vaseline lens panning back on the so what kind of thing. An interesting place maybe to exit is the why do we care? How do we make use of this in our own work and moving ourselves forward as a field, as a science? And I think there are a lot of ways. These would constitute whole new episodes. But, for example, higher degrees of freedom are always good in terms of power. We, all else equal, can show that there's higher degrees of freedom with greater power. We use degrees of freedom routinely in model comparison. So we often teach about, we have model A and it has 10 estimated parameters, and we're going to remove 3 of those and estimate model B. So it's more restricted. And that has 7 parameters. And 10 minus 7 equals 3. Our comparison test has 3 degrees of freedom. And going back an hour from what you were talking about, we evaluate that with a chi-square with 3 degrees of freedom. Well, what are we asking? Does the removal of those 3 parameters do inferential harm to our ability to reproduce the characteristics of the data that we observed? We use degrees of freedom in a multi-level model. It's a constant source of confusion when we look at fixed effects and students pull their hair out, because why do you have 1,100 degrees of freedom for some predictors, but you have 22 degrees of freedom for another predictor? Well, the reason is the 1,100 degrees of freedom goes with a level 1 predictor that is a characteristic of an individual. The 22 degrees of freedom is associated with a level 2 predictor because you only have a smaller number of groups or schools or classrooms or whatever. You want to bend your head? Go to Satterthwaite or Kenward Rogers. And you know how many degrees of freedom you have with Satterthwaite? 11.876. It's like, I'm sorry, what? So funny side story, Bauer and I were teaching at a conference. A very bright, sweet young guy came up, postdoc, had a name badge on, last name Satterthwaite.
No.
And I said, I'm sure you've heard this before, but you share a last name with a very famous statistician. And he said, yep, that's Grandpa.
Wow.
And I met the grandson of Satterthwaite. We're not going to get into that rabbit warren, but what that was is, well, the 2-group t-test, when you do N1 plus N2 minus 2 to get your degrees of freedom. Why? Because you're paying the Reaper $1 for the mean in group 1 and in group 2. Back in the 40s, Satterthwaite leaned back and said, well, wait a minute. We're assuming homoskedasticity and equal variances, and we have sample size going into each of those calculations. And what if we need to make some adjustment for that? And he has this incredibly clever way of getting what are sometimes called fractional degrees of freedom, which is an estimate of the effective N. And that drives people crazy to no end as well. And we had Knuckles on to talk about small sample, multi-level models.
That's Dan McNeish.
Dan McNeish. And there's a thing in multi-level model called Kenward Rogers, which is much better suited for small n. But you estimate the degrees of freedom. You don't calculate them. You estimate them based on the characteristics of the data.
Yeah.
So talk about tentacles that go out in every possible direction in what we do. The RMSEA in evaluating fit and structural equation model, that adjusts for degrees of freedom. It is the misspecification per degree of freedom.
Yeah.
The BIC, the AIC, they adjust for number of parameters estimate. There's a penalty assessed. Oh, dude, this is everything we do in our day jobs is impacted by degrees of freedom.
So if I may then, just to recap some of the critical things from degrees of freedom, the Cheesecake Factory has too many options. You have to pay the Reaper $1.
And I need a 152% to get a B minus. If you get those 3 concepts, you're golden.
I'm feeling it. Well, I hope that this conversation around degrees of freedom was useful for people maybe to understand them a little bit more deeply rather than just kind of saying, well, we subtract 1. It's more complicated than that, but it also makes a lot of sense. So I hope that we help people to gain a deeper understanding.
Thank you, everyone, for your time. We always appreciate it. Take care and stay safe.
Bye-bye, everybody. Thanks. Thanks so much for joining us. Don't forget to tell your friends to subscribe to us on Apple Podcasts, Spotify, or wherever they go to escape some of life's constrained dimensions. You can also follow us on Twitter, where we are @QuantitudePod, and visit our website, quantitudepod.org, where you can leave us a message, listen to past episodes, and lots of fun stuff. And finally, you can get cool Quantitude merch from redbubble.com, where all proceeds go to donorschoose.org to help low-income schools. You've been listening to Quantitude. If we were a type of machine learning, we'd totally need to be supervised. Today's episode has been sponsored by the quadratic term. Just add it to a linear term, and you can pretend you've got any nonlinear function you want. And by reverse valenced questionnaire items, because it's much more valid for the scale as a whole when respondents are kind of sure that they don't not strongly disagree. And finally, by Kenward Rogers. Man, I love his early stuff. You got to know when to hold 'em, when to hold 'em, know when to fold 'em, when to fold 'em, know when to walk away, know when to run. You never count your money when you're sitting at the table. This is most definitely not NPR.